This is very exciting. Hi, this is Dale Peterson, and welcome to the Unsolicited Response Show. My guest this episode is Marina Krotofil. Welcome to the show, Marina.
Hello, thank you for having me.
Well, it's so good to see you. It's been a long time, and it's hard for me to believe I haven't had you on the show before. I think this is your first episode, if I remember, although maybe I had you on 8 years ago or something.
You did. We have a podcast, but it wasn't just voice.
Yeah. Okay. Well, it's good to have you on the show. To give a little intro for Marina, she has been in this sector for a long time. She's one of the original researchers. She now is an independent consultant and researcher. She's on the Black Hat Review Board. She does some work for the European Union. And Marina, I guess one of the things that we might want to touch on a little bit at the beginning is that I guess one of the reasons you moved to be an independent is so that you had time to do research and support the I guess research into the cybersecurity issues in Ukraine, being very close to your heart.
That's right.
So what are you doing? Can you tell us anything about what you're doing or you've done there?
Yes, I can do. I can say a couple of words. So, in October 2021, before the war, I was hired to work on a lot of national scale contracts in Ukraine, very close to Ukrainian government. There was really fascinating scope of works like training projects, building a national test bed and national curriculum for upskilling the people. Actually, a lot of those funds were coming from the USA, which we are very grateful, like upskilling people and so on. And unfortunately, as you know, like the war has started. So I spent the whole December in Ukraine, and I left my home like flip-flops and pajamas because I was supposed to return, which I could not anymore. And in December we had a fantastic grid war exercise conducted by SANS, and where people in Ukraine have showed like fantastic preparedness. That was really very competitive and wonderful exercise. And unfortunately, due to war in Ukraine, we could not really proceed with those projects, and the priorities started being completely different. And before the war, I was actually commissioned by the National Security Center to conduct practical not hands-on, but very pragmatic and tactical training for all owners of critical infrastructures, from nuclear to railways and anything in between, to tell them what the cyber-physical attacks looks like, how the attackers will be doing, potentially executing such attacks, and how can they recognize them and how they can limit the opportunities. We've done this literally a couple of days before the war has started. And since to my and basically the beginning of the war was so messy, nobody was prepared. There was no nobody's prepared for the war. Nobody. There is no platform where you can coordinate the task, where you can see all the needs and so on. So the people of Ukraine has built literally communication networks and Signal and WhatsApp, and we were distributed the tasks and working on them in the way how we could. In the first couple of months, we found an airplane from USA to Ukraine to bring some goods within 2 hours. We've changed the laws how to bring certain goods in Ukraine, and how to make the customs much easier and so on. So there was, and for this reason, I realized that I also participated. Yes, we are not still touching on the cyber part of the things, but at the beginning there was not only cyber, and just because I could be useful on so many occasions, I realized that it's very important for me to have a little bit of freedom and flexibility and time to dedicate to the war in Ukraine. And this is why I decided that I will stay independent for a while, which goes pretty well. And if you to speak a little bit about the cyber, we all know about IT Army of Ukraine, which do their part of the work. And there is, of course, Ukrainian CERT, who does fantastic work together with Microsoft, CrowdStrike, and whatnot. But there is also other units which work, completely closed. And let's say I have my specific channels and people with whom I communicate. I'm a civilian person, so obviously, I cannot conduct any offensive operations. I can do with defense or with information. I can be consultant. And for example, at the beginning of the war, one of the prominent maybe events was that I helped to analyze what cyber-physical attacks with really kinetic effects, dramatic kinetic effects, can we potentially expect. And we've worked through the long list of possible scenarios, and in most cases, I was surprised even myself that once you start thinking about this pragmatically, then you understand that almost none of those scenarios which you're actually afraid of are not achievable by the cyber means, because there is a safety, there is this and that, too complex and so on. And we even see this, for example, on the railway. For example, one of the desired scenarios is to stop the movement of trains. But there is no cyber attacks which will stop a movement of train. There is tracks, and there is a train, and there is a driver. So it doesn't matter how much you will remove. Even if you remove the signaling system, the trains will still be going. So it can be only disrupted by the physical attack. So we have to go to those scenarios, and we've realized that majority of most of the sabotage with those effects will be kinetic. And it was very helpful because it helped, for example, Ukraine not to waste resources on what does not need to be, addressed, and focus on those which need.
Let me ask you one other question on that. I think that most of us in the United States were surprised, especially we have most visibility on the power, I think, in the OT cyber world. I think most of us were surprised at how great a job they've done of keeping the power up and running. I think everyone expected there would be more outages, not just due to cyber attacks, but also due to bombs dropping, sabotage, all sorts of things like that. Did that surprise you at all? Because you're a lot closer to it than I am, but were you surprised that they've done such a good job keeping the power on?
Very much. Very much. And I think this is something what I'm sure the whole world is learning from this, how much resilience are there in the industrial systems. Not only the power, but also water. In certain events, they were always able, if there certain pumps are out, certain water supplies are out, they were able to reroute something. Even when I read, I'm not that much into the power engineering or water engineering that I could understand, but they could actually recover water supply because of the so many redundancies. So I guess we are all learning from this. And it's true that sometimes I definitely read an article where one specific place of power infrastructure was bombed 6 times until it became unrecoverable, because each next time the engineers were able to reconnect and return the power. And what we've noticed what Russia was doing, they never targeted only power. It always was power, water, gas. So they were targeting at a humanitarian crisis. So you need to get so that basically any utilities would be there to really cause a humanitarian crisis. And this is where we've seen people melting water and chopping woods, cooking food, and so on.
Okay. Well, I don't know if there's a non-awkward transition, but I'm going to transition us to the reason that I asked you, but our thoughts and prayers continue to be with the Ukrainian people and their effort. The reason I asked you on the show was you wrote a paper recently. It came out in May called Industrial Control Systems, Engineering Foundations, and Cyber-Physical Attack Lifecycle, that was amazingly detailed and quite interesting. And I wanted to talk to you a little bit about the paper. Just so we're on the same page, when you say cyber physical systems, I'm viewing that as essentially the ICS plus the process. Is there a different way you would characterize what you mean by cyber physical systems?
No, that is pretty accurate.
Okay.
I think, and the reason why I called I wanted to have this cyber-physical in there, and I think I make a remark in my technical white paper, is that majority of the principles, or let's say almost all the principles which I'm explaining in the paper, they are applicable to any cyber-physical system. So even if some engineers maybe like don't do continuous processes, the principles, and I verify them on different types of cyber-physical systems, they are applicable to pretty much any cyber-physical system.
Okay. And, I've known you for a while. It was probably like 2013, 2014 at S4 when I saw you do some work with Jason Larson. But what got you into this cyber-physical realm? What was kind of the instigator that got you interested in? Because it's been a major focus of yours for over a decade now.
That's right. Like 13 years. I think two factors. So I initially get into this field thanks to Ragnar Schierholz from ABB, who sent me this NIST standard. And because my background is in telecommunication systems, which are so similar to industrial control systems, it's distributed application, signal processing, real time. So I suddenly was at home. Plus, I have a strong background in mathematics and physics. So it's just like was everything what I know and like is in this field. And then there was, I think I would say, combination of my professor Dieter Goldman and Jason Larson, because, like as everybody else at that time, I tried to move like, let's address this threat through the cyber layer. Everybody was going in that direction. And my professor said like, well, no, if you go to that direction, I don't see this being a potential. And if you insist on going there, I will discard your PhD. So I definitely did not have a choice but to go this direction. And then I met Avery Leverett at CCC, and who introduced me to the breakage vault by Jason Larson. And from that moment, it just was no way back. It's just like I fall absolutely in love with that area, because as you notice, my focus has always been offensive person. So I'm using my offensive security knowledge and mindset to build defenses. But being in this inoffensive field, it just gives me a joy to my brain, if I may say so.
Yeah, it seems though, and that professor is interesting. Your PhD professor, that is very clear motivation. But I haven't seen a lot of people pursue this field. I see a lot of people, even with backgrounds in physics and engineering, they focus on the ICS part of it, the cyber part of it, and much less on the physical part of it. Even when I look at the papers I get for S4 this year, I see very little what I would call post-exploit. You own the system. Mm-hmm. What am I going to do now that I own the system? How would you characterize the state of the community's understanding of this today? Do we get this, or are we still lacking an understanding of the difficulty of this?
Thank you so much for this question. I really appreciate it, because this was one of the reasons why I put my personal time and effort, and I'm even hosting this paper at my personal cost, because I want to bring this knowledge into the community. Many times people been asking me like, Marina, if I would like to go into this field and basically do research similar to yours, where do I get the knowledge? And I say, like, which is the book? Like, there is no book. This was like people have to understand that I've been doing it for 13 long years. And many of those which were, let's say my first work on cyber-physical exploitation going through this life cycle, it was 1.5 years of effort and a lot of sleepless nights, weekends, and so on. It was a lot of sacrifice. So developing these foundations, because there is no literature, nobody's guiding me. So I think because this field is so multidisciplinary and you have to learn so many fields, control engineering, process engineering, embedded systems, and mechanical engineering, and everything in between, plus having a lot of persistence and desire, because unless you're super interested, you will not stay in this field. And that is the reason why we don't see much works. And I mean, let's be fair, like, let's say let's speak about Jason Larson. He brought, when he, in 2006, when he presented this first Cyber-Physical Attack Lifecycle, which he did not describe, so that's why I have to formalize it myself. He's been working many, many years to come to that point. And I remember at that point, I was a little bit like, let's say, I was still younger and I was a little bit jealous. Why Jason Larson is so much appreciated and I'm not so much appreciated. Like, I'm also doing the cool work. And he was always telling me, well, I've been in this field for so long and now I understand what he means, because now I can appreciate the amount of work, years of work he put to be at that expert. What we see as a 45 minutes talk at S4, it's years of hard work.
Yeah. Well, you kind of answered one of the questions I was going to ask, because you took 1.5 years, a year and a half to write the paper. And when you look at this paper, I saw it had 241 references. So it's very wide. I guess they're not quite footnotes because they weren't at the bottom of the page, but essentially 241 footnotes that document where various facts came from. So it's clearly a lot of work. So I understand now why you wanted to write the paper. One other question before we get into it. You've focused on offense, as you said. Do you see now with, I don't know if you've been tracking what's happening with the CCE, the cyber-informed consequence-driven engineering, or CIE, where they're starting to say, we need to do this from a defensive standpoint, that we need to understand the system and say, if someone owned the system, what could they do? Which essentially is what you did in this paper for a very specific example. Do you see this capability that you're describing in the paper and that you've developed over the years? Do you see there being a defensive application for this as well?
Absolutely. The reason why I wrote this paper is, you see, like, I may be lucky enough that I had an opportunity in my career to work both in offensive, and then I had a chance to apply my offensive knowledge to defense. But there is many people who really look at it from the engineering perspective, and they just try to make system more robust, including cyber attacks. However, developing this offensive mindset and knowing exactly every single step, every single milestone which the attacker needs to achieve is so important in order to understand, did I miss something? And this white paper is solely to try to develop this mindset in the, let's say, pen testers, red teamers, engineers, whoever will look at it, governance people. So I want to bring them this knowledge so that they will become better defenders. Did I consider everything? And developing this offensive capability, I mean, let's say, first of all, it's a mindset to develop. And secondly, I'm testing a lot. I'm not making hypotheses. I'm testing everything. And sometimes this test, in most cases, test takes much more longer than developing the capability. Is it stable? Is it working? In which cases it does it, which not, how many edge cases, blah, blah, blah. So analysis takes much more longer time. And then processing this, and like in my white paper, I would say there is no water. So every sentence carries information. But that information was devised via the long hours of testing and processing and critical analysis. And that is what I bring to those people who use already building the system, like, hey, use this and build the defense, let's say, resilient, robust, and defensible system.
Yeah. I mean, I know you've done research for a number of years. You're doing consulting now. I could actually see that you'd have more people, more asset owners that would need this skill set for defensive consulting than offensive. Offensive is showing it, but I think a lot of asset owners could use people like you who understand, maybe think a little more, how could this system be attacked? What did I not think about? So I think that's going to be a growing field. I'm hoping you might want to take a look at the CCE, because it's the first effort I've seen where they're actually saying, we need to look at the process itself and make it so that cyber attacks, even if you completely own the system, couldn't do the really bad things. So you might get a little hope out of that.
Absolutely.
Let's dig into the paper, though, okay? So I thought I just want to give a shout out to Chapter 2, ICS Engineering Foundations. To me, if you are, especially if you're coming into ICS from IT, I think this is an excellent chapter. You know, you get down to control loops, you get down to different types of systems, some really nice charts. And as you say, there aren't wasted words on it. I would say the only thing the IT person might not like is the math. I skimmed over a lot of the math on the control loops, but you can get the gist of it, the physical side of the cyber physical, much better than I've seen in it's one of the best I've seen. So I would highly encourage people to read that. But you wrote in that chapter, the concern for physical consequences puts cyber physical system security apart from the science of information security. So you say the cyber physical system security is apart from the science of information security. I wondered if you really meant apart, or because I would think there'd be a pretty big intersection or overlap between the two. I would say there's additional things, but do you really see the study and protection of cyber physical systems as separate from information security?
Yes and no. There is absolutely gigantic overlap because, for example, so especially recently, you're absolutely right that OT field is maturing and people start, basically, they don't want anymore to do pen test in terms of like, can I get through the firewall and get into the control zone? They don't want it anymore. They want look at my system holistically and how the attackers potentially can discover my system. And discovering the system, it means, for example, information protection, where all of my information is residing, because that is the first what the attacker needs. So there will be components, large components of the cybersecurity, which are traditional to the IT security. In my paper, I mostly focus, because again, I did not want to repeat IT exercise or IT security. I go and studied in the other book. I just kept having the physical, focus on the physical, on disrupting a physical process. And basically then when we say but cyber physical attack, we are meaning the attack which has as a consequence physical impact. It can be just economical. You just degrade the process and it is just, like, let's say it's cost you more to produce. However, on the path to that attack, there will be a lot of elements of IT security. Absolutely.
Okay. I think if I was to pull out two sentences that I think encompass the whole paper, you said, it is often claimed that once communication security is compromised, the attacker can do whatever she wants. And I'm probably guilty of saying that as shorthand. But then you say, after that, process physics and built-in safety measures might get in the way of the attacker. And I'd include I/O in there too. Maybe that's what you mean by physics. I mean, if you don't have the I/O to turn something on and off, your cyber attack is not going to allow you to turn it on and off. But why don't you just explain that a little bit more? Because I think that's where people without an understanding of the physical side really fall short in terms of what is possible. So what do you mean by process physics and built-in safety measures?
Oh my God, this is a great question. I have a very good and digestible example for that. And I'm grateful to the Singapore University of Design and Technologies for assisting me with that experiment. So, for example, for a long-term, so for example, let's take water utility. Yeah, very emotional example because, oh my God, somebody can poison the water. The good news, the poisonous water will never leave the utility because there are chemical analysis, and only until the water is fully, let's say, safe, it will be fed into the pipelines. So, I mean, really poison the water would be near to impossible to execute. However, for example, let's assume we want to interrupt water supply. And to interrupt the water supply, we need to break the water filters. If we cannot filter it, we cannot basically clean the water. So we implemented the attack because they have a test bed on trying to kill the water filter. So to kill the water filter, you need to study the manual. What is the harmful condition to the filter membranes? I found those which are implementable remotely, because many of them are not implementable remotely. Then we needed to analyze control logic. We've just basically followed the completely like black box. I'm a known attacker. I want to achieve this goal. It was really so gigantic amount of effort, but eventually we compiled an exploit, which was not easy because we have to overcome the safety interlocks, which were in the control logic, which is possible to do. So eventually we were able to implement attack where we made 2 exclusive workflows going through the water filters, because we needed to raise the pressure inside of filter to break the membranes. But even when we run them with the highest power possible, the largest pressure which we could achieve was 1 bar. And the membrane break at 2 bars. So it means that it is a fantastic and perfect valid damage scenario. We get access to the infrastructure, we implemented the exploit, and we were even successful in implementing attacks. But physics of that infrastructure did not allow us to achieve the pressure we need to break the filter, the membrane. So, well, bad luck. And that is what I meant by the, and for example, in that case, if there would be, example also as an exercise when I was training engineers in Ukraine, and the engineers are fantastic. They immediately saw which physical protection they would put in place, that those exclusive flows would never be possible, and they were surprised that even that interlock was implemented in control logic, which was not easy to overcome in terms of exploit because it's a lot of flags to manipulate. But yeah, so it's basically, yeah, it's not always that the attacker is not almighty. That's what's my conclusion.
Yeah, and we had a recent episode with Gus Serino on the Oldsmar. He's a water guy, and we went through step by step on the Oldsmar. And he even gave it was a really simple example where there were probably a lot of places where it would have been stopped, but there was a pH sensor, probably, or there was a pH, some logic in the PLC that if the pH exceeded a certain level, shut down the pump. And he said a real simple way of dealing with that risk would have been to have an external pH sensor directly hardwired to the pump, not in the PLC. And in that case, even complete control wouldn't allow you to deliver water at too high of a pH level. And I think there's a lot of that we don't think. But then on the flip side of it, one of the things that's been really interesting, if you think about the cyber-physical, is we've seen a lot of outages of control systems caused by ransomware on the IT network because they haven't been able to run their process without it. So they haven't caused things to blow up or equipment damage or things like that. But in theory, if someone got to the IT network, they could just, from a pure cyber standpoint, shut it down. They could brick a bunch of systems or require them to be rebuilt. What are you, I guess I haven't really thought about it from the cyber-physical standpoint, but how big of an impact do you think not having the ICS would have on a lot of these processes that you've been investigating? Would it cause an outage?
Again, so if you take the example of Belarusian railways, it did not have an impact. For example, yeah, the trains still can go. They go slowly, but they go. Right. However, for example, if you take something as an assembly line, which mostly, like, for example, if you take car production, an assembly line, and just all of them work on the principle of just-in-time production. And just-in-time production, that's logistics which manage in the IT level. That's it. The outage would stop everything, the whole part. Plus, it will take cause so many inconveniences in the city, because a lot of basically cars will be just stopped where they are because, like, well, let's say that probably will be some chaos with delivering goods and so. Maybe even better example, I will tell 2014 in Ukraine, when I think, or was it executed in 15? I might be confused as it was 14 and 15. So the threat actor just simply blow up their exploits in the railway IT network. What has happened is shows that once there were several threat actors, one started basically destroying their exploits, and there was few threat actors, and everybody started destroying because they just like, what's happening? Like, let's all blow up. The whole basically systems were out, so you cannot dispatch any wagons anymore, trains, nothing. So a lot of ships came into the ports and a lot of needs to lead, but there is no trains coming to take and bring the goods. So there was a chaos in the port, a line, a queue, challenges with the delivery supply chain and so on. So it took a lot of time to untangle this basically bottleneck. So there was a known case which was described in the newspapers in context of the BSF, where they also had an outage of the, let's say, SIP system, which schedules all of this delivery of the supplies, and the queue of the cars. It's just crazy how many, let's say, cars are coming per day through a factory. They had basically the traffic jam in like several kilometers, like if not 20. So this is absolutely true. And for example, also, for example, this is where me as an engineer, as a defense engineer, I always tell, like, you should have at least either mirrored function for scheduling in your, so I think, let me rephrase this. So within your OT perimeter, you should include all the functions which allow you to function at least for a certain period of time. So you should be always able to disconnect. That's why we have this DMZ zone, which is supposed to disconnect you, let's say, have a buffer between this untrusted zone, and have at least certain amount of functionality, mirrored, copied, whatever, which will allow you to function even if IT level is not available anymore. So that is what my recommendation, if it is expensive for you.
Okay. Well, let's move on to, so chapter 3, you give a detailed example of a vinyl acetate monomer process, which really, I mean, this is going to be deep for a lot of people, but if you want the gory details of a process and how it could be handled, and you talk about the denial of service attacks, stale data attacks. So I think there's some things in there that even if you don't want to know about that process, you can gain from. But one of the things that was most interesting in there is that you outlined safety constraints and operating constraints. And it would seem that would be something that would be important for anyone looking to do offensive or defensive work to highlight on their process. So maybe explain a little bit what you mean by safety and operating constraints and what the differences are.
Right. So operating constraints, this is where you typically would get an alarm. So for example, in this specific model, we did not have financial alarms. So if you look in the standards, sometimes, so even within the normal operating envelope, so if you are not even violating any operational constraints, this is where it's already become maybe not so pleasant for the equipment, maybe quality of the product is degrading, too much losses and so on. But within this, even some industrial standards also suggest you to put in to configure certain financial alarms. So if you're operating at this level or this point of sensor, like pressure, let's say, you're already not optimally or unpleasantly suboptimally in terms of finances. So, but operation, typically you will have the notifications comes at the operational alarms, like, okay, if the certain value, flow, temperature, pressure exceed this value, then operator will get a notification and they will start reacting. And so basically I try to, if they start reacting,
I can pull one of them out here. So you said, for example, if the liquid levels in the vaporizer, separator, absorber base must operate within the limits of 10 to 90%. And if you don't get that, then you'd get an alarm. Whereas on the safety constraints, those seem to be tied to things that would shut down the process via interlock.
Right.
So if the O2 concentration was too high, must not exceed a certain level, then it would shut down the process. I would think that almost like the water example I mentioned before. One of the first things you'd want to do if you see those safety constraints is see, is there a cyber way to change or disable that safety constraint? Almost like we saw with Triton, the attempts with Triton.
I have 2 points to say. This is like really brilliant example which you just read. So one point also from the attacker perspective, you see, on one hand, I tried not to, let's say, trigger those operational alarms because I didn't want the operator to pay attention to what I'm doing. So I was operating within the operational window. But secondly, if you will start triggering operational alarms, it makes already the physics become suboptimal. And with time, these suboptimalities in the physics of the process accumulate to the extent that it's becoming unsafe to operate the plant. And the plant will go into the safety shutdown before even the attacker reaches the goal. And this is one of the scenarios where I failed to implement another example, where if you, for example, let's assume I will be triggering operational alarms, but I will suppress them. And I'm an attacker, I can do it even on the sensor or on the PLC. But eventually, the physics within a relatively short time, the physics of the process degrades to the extent that the plant goes into the safe shutdown, and I still did not achieve my attack goal. And this is what, for 2 reasons, I decided not to violate operational constraints. However, and the second point which you highlighted, and it's brilliant again, that yes, of course, the attacker can go also in the safety system, and this is what we've seen happening in the Triton case. We all know, any engineer knows that having a dual homed safety system, like it's an engineering workstation, is the worst practice ever. It does not happen anywhere, honestly. Maybe when I've done maybe 50 plus audits of chemical and petrochemical plants, I have not seen it ever. However, the typical scenario which we will see is safety and control PLC communicating with each other via the Modbus. Either Ethernet or serial, doesn't matter, but they communicate. And just right now, just this year, the brilliant US vessels came up with deep lateral movements, basically techniques how you move laterally over the industrial protocols, including serial. And he showed that you can actually fantastically move laterally from the control PLC into the safety PLC, get foothold, get stable exploit, and basically, as you say, change that value. So if in the past, including me, I was considering this being a safe practice, I would, on the audits, yes, fantastic, completely, let's say, we consider it secure because it's only, if available, only to super experienced attacker. Yours vessels now has shown, no, you don't need to be super experienced to actually move laterally through this link. So it's no longer safe. We now need to introduce new practices, how we defend this link. And I really highly recommend every safety engineer who is protecting or designing protections for safety systems or interaction control and safety systems to read that paper.
Yeah, and that's been something though for a while, that you do not want to allow a compromise of your control system to affect your safety system. Unfortunately, the Logic project said it was okay to interconnect those 2 systems. The first time they did it, the second time they did it, the third time they finally wrote the report post Triton, they came out a little more serious about that. But you have big name vendors that talk about integrating these systems, and even some asset owners that have huge investments in these integrated systems that try to say they're okay. I'm with you. To me, it just seems crazy that you need to have, if they do need to communicate, you can have a unidirectional, you can have a read-only capability or something like that, but it is a huge issue, I think, right now.
Yes and no. So on one hand, yes, you're absolutely right. On the other hand, for example, I'm a big fan of secure architectures. If you decide, like for my, let's say, safe, it's easier for me from cost perspective, from maintenance perspective, I want integrated system, DCS, safety and or control, fine. Then consider like this is a big risk, so I have a fantastically big risk. Then build a really very strong, controllable, defensible perimeter. have a proper layer segregation, have a proper DMZ, highly controllable, implement monitoring, and so on. Then basically, plus, like no remote access directly in layer 2, let's say, only through the DMZ, maybe even through the corporate and so on. So then defend your perimeter and monitor it in there.
Well, we can agree to disagree on that.
Of course, of course.
But that's fine. That's part of the fun. Now, we're almost out of time here, but I want to hit, at least one more really important thing. Chapter 4 is also great. There's sections on classes of cyber-physical attacks, equipment damage, production damage, compliance violation. I think that's a really good section. But the one I want to make sure we hit is your cyber-physical attack lifecycle. Mm-hmm. Which you mentioned earlier. Jason sort of started it informally, and you've formalized it and also added to it. The various steps are access, discovery, which is kind of like reconnaissance, but reconnaissance plus, I would say, control, damage, cleanup. The one that really surprised me and I hadn't thought about is that control step. Can you maybe define what you mean by control, that because that was a new one to me, what you mean by that step?
Right. So control stage. So this is, again, I will come back to this, my water example. So basically discovery and process comprehension, it's about collecting the static information about the process. However, physical process is a dynamic system. So and this is why it's basically, this is what is a new dimension, let's say. So you need to understand the dynamic behavior of the process. So because if you change the pressure, or the temperature pressure is changing. If you make some attack in one part of the process, it propagates in different parts of the process and may be visible to the operators, or basically evoke compensating reactions from the process physics. And so it's basically all about discovering the physical behavior of the process. If I trigger a little bit the process, change, for example, position of the valve, how much it will change, little, lots, and so on. And the best example, again, if I return to this water filter damage scenario, the point is that no information, no paper-based information, and no even logic of the PLC will tell you what level or what pressure you will be able to achieve once you let this water run through the filter. That value can only be discovered through the dynamic testing on the live system. And this is why I wrote in my paper as well. So a lot of scenarios can be prevented by simply preventing attacker from having a persistent long-term access to the production environments, because those scenarios needs to be tested. There are other examples. So for example, I was testing this attack life cycle on the traffic light system. Yes, when it is just a square, simple crossroad, we know how it works, yeah? But majority of the crossroads, they're interesting, they're very complex, yeah? And there is no, if you just change one light, you don't know how everything will change. And you will need to test all the possible scenarios to know, if I change here, how everything else on that crossroad is changing, and what needs to be sequenced so that I will receive that state of the traffic lights, which I need. And that is what can be only, well, in this specific case, this can be also discovered from the state diagram, because this is, I now know traffic light system, so I know they have, I forgot what it's called, STT, state blah blah diagram. It's possible to recover it from there, but in majority cases, I guess you got the idea that you need to try on the live process.
Yeah, I never really thought about that, because I thought in the recon phase, even if you did extensive recon where you got a lot of paper, you got all the lists of tags, and you understood the whole, you could draw out the whole process, that would be enough. But that was really kind of a learning to me, that even if you know that, you're not going to know this dynamic interaction. And then the other part that was very interesting is, and this is where you added a little bit, was, I'm sorry, do you want to say something?
Yeah, I just wanted to add another piece of information. Nobody knows that Jason Larson destroyed 11 barrels until he got the 12th fail as he wanted in his very famous 2014 experiment. 11 barrels he needs to destroy until he got it in a controllable way. And he found the condition how things work in a nice way.
Was that at Black Hat or DEF CON? Where was that?
It was Black Hat.
Did they know that that was going to happen?
Yes, they did. They did. So he repeated the experiment at DEF CON. He could not repeat it at Black Hat. But in reality, until he arrived at the magic of those numbers, which allow him a very nice experiment with this, like, let's say, using effects, he destroyed 11 barrels, and each of them will cost a lot of money. So arriving at that fantastic amusing experiment was very, very costly. And that is what people don't understand.
Yeah, I don't know that I would be able, that my insurance and my venue would allow me to do that on the S4 stage. That was a great demo, though, with that kind of exploding barrel, water barrel. The damage loop that you added was another thing that I found interesting. So you understand the system, you go through the control to understand the dynamic parts of the system, and then you had this loop where you had the damage was done, but you also had a little loop that said obtain feedback, prevent response. Or maybe I got those backwards. And this is something that you talked a lot about that we haven't seen as much, except maybe with Stuxnet was doing some of this, but even you could even say some of what Stuxnet did was kind of basic, just replay, that sort of thing. It as Ralph has said, once you put on the brakes on that centrifuge, the noise would have changed drastically, and you would have known, if you were anywhere near that, you would have known that the centrifuges weren't spinning. But this idea of saying, I want to affect the process in a way that they don't know what's going on. And you even had something you said, plant shutdown is risky for the attacker as it may instigate an investigation. We haven't seen a lot, or we haven't at least known a lot about this. Maybe it's happening and we don't know. How hard is this to achieve? And do you think this is something we need to be ready for in the future?
Yes, so maybe I will provide also example, one of the recent works by Nozomi, where they've been talking about, wireless, this locating systems. It was also Black Hat, because you see, I work a lot, of course, with researchers in the background. Yeah. So that's something what I don't talk about much, but when they were also implementing the attack scenarios, I told them, like, well, but the operator will notice that you're changing the location, that the person was suddenly here, and then you move it in there. They will notice something has changed. If you want it to be unnoticeable, that is where this prevent response. Then you need to implement a curve where the person change the position where you want to be in a believable pattern. And this is why it became, this is the paper like on my table, I'm still working with it. This is where they implemented specifically, and it is described very well in that paper, that they've learned their believable normal patterns. And when they start basically modifying and basically and making the operator believe that everything is fine, they move those people in the safe position, in the believable pattern. So that is very important. That is to prevent response. And basically, yeah, and this is which also will prevent instigation, let's say. Instigate. I think it will delay them from thinking that something it was caused by a cyber, because humans were believing in a normal way, something then, but they were not. They will start thinking that probably, let's say, there was some failure in the hardware or the signals and so on. They will not think it is a cyber, because everything looked like normal. And this is where prevent response and obtain feedback. This is two of the most difficult parts in designing exploits. And I think I also say in my paper that any scenarios which require these two conditions to be there probably are the hardest to execute. And this is why we should more concern about those like so-called easy button attack, which the term which was coined by Reid Whiteman. Yeah, so it's basically, if you change the condition of the process, you know reliably it will fail in the way you intended to fail. You don't need to monitor. But for example, even in the case of the JSON attack, in many cases where, for example, this implosion is possible, engineers know that it's possible. There will be mechanical this vacuum breaker. And if he will try to implement it, the vacuum breaker will kick in and his attack won't succeed.
Mm.
Therefore, you need to have a feedback loop to to know, am I successful or not? Because there is no roundness sensor, which will tell you like, well, the pipe is no longer 3 centimeters in diameter. So he was searching for that indication of vacuum breaker in the sensor signal, in the pressure sensor signal. And this is where the companies like Uptake and pretty much any industrial company now do use AI to look at this in the sensor signals. They look of signs of equipment deterioration. You use AI to so this is the same what basically the attacker needs to search or basically develop this knowledge, let's say, the same. So yes, these two conditions. So the reason, so initially those two stages were not in the attack life cycle, but after I applied it and I worked with a lot of exploits, and with time, with my experience, I realized that these two are so important, so critical that they need to be separate stages. And this is I've taken them as a separate stages.
And I would suggest to the listener that section 4.6, I think, is a really great session. If you're just going to read a couple, that's where you talk about the easy button. And I think that that discussion is at a high enough level that you don't need to understand all the control loops in engineering and mathematics to understand this idea of different types of attacks and the hiding of attacks and the attacks that are more just an instant in time and are easily discovered and easily accomplished. I thought that was a great section. I thought, for me, that the highlights of the paper were section 2 and section 4.6, although there's good work throughout the paper, but I think any reader could benefit from those two sections, and then they can kind of decide how deep they want to get into your process and all that. And as I mentioned, it's definitely a paper that is well researched. There's lots of papers. If you find something interesting, you'll be able to read something else. So great work, Marina. Really nice job.
Thank you.
Is there something else you want to highlight about it or about this line of work before we end the show?
Yeah, so for example, I understand when you say that, like, well, there is some chemistry, there is formulas in mathematics, and you don't need to understand them. They are there for illustrative purposes. For me, of course, like, to make my conclusions and my analysis, I needed to go into the depths of that. But for the reader, I've tried to write the paper in so understandable ways that any person without any previous background can read through it, get a very good feeling that they understood, and kind of start reasoning better about this type of attacks, scenarios, about these environments, attacker efforts, and so on. I want to, basically, the white paper was developed for people, so those, for example, red teamers, or maybe threat intelligence people, they want really to go into the details. For others, I really want them to develop a high-level feeling. So I would really, in my personal opinion, that people should be able to read through this probably through the day and understand sufficiently enough to get a good feeling and intuition about this field.
I'd agree with you, and I'd say even the parts that I skimmed over, I would say they help one understand the complexity, which is kind of the basic point, is that you have cyber access. You just can't, for example, affect product quality very easily. It's not going to be a simple measure. Or if you want to cause some equipment damage over time, it's not going to be a simple thing. It is a long, detailed effort, and going through all the steps in a real world example helps drive that point home as to how much work it takes to achieve that, as opposed to the easy button attack. So I think you really hit that. Marina, if someone, I don't know where you're active these days. Are you active on Twitter/X, on LinkedIn? If someone wants to keep up with what you're doing, where are you most active?
Well, I've realized that Twitter these days has very strange, like mechanism, which tweets they highlight. Sometimes you write something very important and nobody even notice it, because it was not highlighted in the field. And then you write some unimportant thing and you get like 150 likes, like, well, it was displayed for you. Why? So it's just like, I could not find so far a reliable mechanism where I should post maybe certain important updates. And this is why I started my webpage, where I will, of course, put this video. But I do read personal messages, or like if somebody would like to contact me, and I would like to start a little bit more active in a little bit more constructive way. As you notice, like I work a lot with different organizations, like, so I maybe not sometimes always have time, but also, like clearly, like what I do takes a lot of effort, and I put my personal time. So I really would, if I write something, I would like it to be noticed. And
well, we'll put a link to the paper and a link to the website in the show notes for people. I'd highly encourage people that want to learn more about the physical side of cyber-physical to take a look at it. And Marina, I appreciate you coming on the show again.
Thank you so much. It was a great pleasure. Can I add some more?
Sure, of course.
Maybe I wanted to also add a couple of words to my appendix. So, like there was a couple of, I put a stale data attack, which I purposely put it there because into my white paper, because Jason did a fantastic work on building and weaponizing this type of attack. And I really wanted to keep it in white paper, hoping that it will be noticed and maybe some people will pick up and research it further, because I find it one of the most dangerous attacks to the industrial control systems, much more dangerous than data integrity attacks. And there is a reason why Jason was doing a follow-up work on my work. But I also put a little bit of extra information in the appendix, because the data security in industrial control system is completely different from data security in the enterprise domain, in IT domain. And certain data security properties are the same, but many are different. And I really want to keep developing this field. I want to more people start understanding the differences and start researching more. And it's all in my white paper. So the reason I just want to re-highlight that the reason why I wrote this paper is because I want to put everything what is in my head out there, so that people maybe start learning more about this field, pick it up, and start developing further, so that we make progress.
There is a lot in that paper. I would say I got through about half of my notes and questions that I was going to ask you, so I had to kind of pick and choose, but there is a lot in that paper, and I'd encourage people to read it.
Thank you so much. And maybe the very last thing that, on my white page, on my webpage, I wrote 5 groups of people who should be reading the paper, and I just provided exact description how can they benefit from reading this paper. And if you will read the paper from a specific, let's say, mindset or angle, you will pick up a completely different information. So description on the webpage, how to read the paper, if you, for example, pen tester or governance person, will help also to read it in a specific way.